Apart from length and diameter, another factor that affects the strength of the fibers is the aspect ratio. Ratio of fiber length to diameter. Large aspect ratios result in stronger composites, but more difficult to orient and often limited by size of the composite itself, right? So how much bigger is the length compared to the dia, right? So this will, if it is large, then the strength will be high, but it will be difficult to orient it. Designers define a critical length, LC, below which fiber provides little reinforcement, but above which the fiber behaves roughly as if it were infinitely long. So this is important, right? That you can have any length of the fiber, but if the length of the fiber is below a critical length, then there is almost no advantage of having a fiber reinforced composite, because, right, it has very little reinforcement. Above which it is good, right? So now LC is sigma F D upon 2 tau I. Sigma F is the tensile strength of the fiber, right? Fracture strength of the fiber, or sigma F tensile strength. What is the maximum strength of the fiber? D is the fiber diameter, of course. Tau I is an empirical constant called wet out that relates to quality of bonding between fiber and matrix, right? The matrix is some polymer material like polyester and so on. And when you put the fibers inside, then there should be some sticking, right? Some sticking of this fiber to the matrix material, like bonding. We will see later on that in concrete also, right? Concrete is particulate, but the sand particles should really stick to the cement. Otherwise, there are two things inside, right? They are not really strong enough. So this wet out will be a term most probably they use in concrete also. So here, wet out, the quality of bonding between the fiber and the matrix. Bonding quality is difficult to characterize. Critical length generally determined by trial and error, right? So we should know the wet out. If we know the wet out, which is difficult to find, then we can define it. But if it is difficult, then this is also difficult, right? So if it is difficult to find out, then the critical length will be by hit and trial. You try 1 centimeter, 2 centimeters, 10 centimeters, and try to find out which is the critical one. If you can find out tau I, the wet out, then you can scientifically predict what will be the critical length. So here, a table of the properties of some common reinforcing fibers: fiber type, aluminum oxide, carbon fiber, e-glass, Kevlar, and so on. Density, tensile strength, specific strength, and elastic modulus, right? So these are properties. It means that, at least for our introductory knowledge of composites, I keep on telling you that if you end up in a company which is actually doing composites, then they will be doing only a few, and for those they will have a lot of data. So within a very short time you will become champions and experts. But here, for our purpose, for this chapter, all the calculations and other things, this table will be enough to give the properties. Let us do a simple problem. For a Kevlar 29 epoxy resin composite, the critical length of 13 microns fiber was found to be 44 millimeter, right? When small quantities of glass fiber are added to the composite to improve wet out, the critical length was reduced to 33 millimeter. Estimate the wet out constant for the composite both without the glass additive and with it. So as I always tell you, that just read it, take down the knowns and the unknowns, and then decide how you will do it, right? So please don't go ahead with the solution. Always, I mean, you can go back 1 page, 2 pages, but this is a very, very simple one, but you just have to, think a little. So let us see. you first of all, right? So if you are listening to me now, then you have already solved it. All right. Otherwise, after the first portion, when I read the problem to you, you paused the lecture, then you did it. So now if you are listening to me, then you have already done it. So the material, the fiber material, right? The fiber material is Kevlar 29. The matrix material is epoxy resin. The fiber has a dia of 13 microns, right? The critical length is 44. So this is the thing, and you can then find the things. Now they say wet out. To improve the wet out, they added some small glass fiber, chopped glass fiber. A small quantities of glass fiber are added to improve the wet out, to improve the bonding strength between the fiber and the matrix. If they did that, then the critical length reduced from 44 to 33, right? So wet out constant tau I, find it for both the cases. So the equation is this, right? The critical length, strength of the fiber, dia of the fiber, the wet out constant. So this is the equation. This is the only equation that you have, and this is the table, right? So Kevlar 29, you have all the values. Kevlar 29, you have all the values. You have for E-glass also, but right. So now first case, when there is only Kevlar, do you know the critical length? It is 44. Do you know the strength of the Kevlar 29? Tensile strength 2.8 gigapascal. Yes, you know it. Do you know the dia of the fiber? 13 microns. So just find the Ti from here, right? So the first case, when there is no glass fiber, only Kevlar 29, then do this. Next time is just you think a little, a small quantities of glass fiber, a small quantities. So when some chopped fiber is there, a small chopped fiber is there, then there is, we have told you, there is no basic changes in the fiber, in the composite, strength wise and so on. So we have added some glass, but to strength and this and that, there it is not contributing. So strength wise, it is still only a Kevlar 29 thing, but the critical length has changed. So you apply the same equation. So this does not change, this does not change, the critical length changes, and you can find out this again, right? So this is it. Therefore, if you now see what they have done, that they find the sigma F for Kevlar, the dia is already given, the critical length is given, you find the thing. Then when you add glass, nothing happens, only the critical length changes. The rest of the things remain the same. So it's a relatively simple one, but if you got confused in how to use the glass value, then it will take some time. Otherwise, it is not a very difficult thing, because if we add any small amount of a chopped fiber to something, the overall strength and so on of the composite is not changing. Here we are just adding some chopped glass to improve the bonding between the fiber and the matrix, right? So you have done a good example and you have some idea. Let us go. Rule of mixtures. The most important equation or theory or whatever you say in composites. For many properties, density, electrical conductivity, thermal conductivity of the composite, we use the rule of mixtures. Simple mixing rule based on volume fractions. This is a very, very simple rule. It is linear. There is no higher degree, no quadratic, no cubic, nothing. But it works really well. When we say it works really well, then it has been used in hundreds and thousands of applications, and the results are very close to the experimental value that we get. So FF plus FM plus FV is equal to 1. So the sum of the fractions is 100%, right? 1 is 100%. FF, volume fraction of fibers. FM, volume fraction of the matrix material. FV, volume fraction of voids, right? So if there are no voids, If there is, for example, there is matrix and there is fiber and no voids, so Fv will be 0. But if there are some voids, right, we are trying to make a good composite by having fibers inside some polymer matrix. So if volume of the voids is not there, then it's a very good strong fiber. Otherwise some voids will be there. So but this is it, right? There is fiber, there is matrix which is the polymer and so on, and there are voids. And volume fraction, volume of this upon total, volume of this upon total, and so on, volume fraction. So this is a very, very simple equation, linear equation, but very powerful, and we use even this in simulations. When we try to simulate the behavior of a composite using finite elements and so on, we still use this very simple rule of mixtures. Let us see now each property. Density of the composite, rho FFF, rho MFM, right? We are then assuming that voids are not there. Thermal conductivity, K of the composite, again KFFF, KMFM, F for fiber, M for matrix. Electrical conductivity, right? Remember in the chapter on electrical conductivity we were using sigma for conductivity. So again sigma F, sigma M, and so on. So density, thermal conductivity, electrical conductivity of a void are 0. You see, density of a void is 0, so it does not matter. Conductivity of a void is 0, so it does not matter. Electrical conductivity, so therefore it automatically goes away. It is not that we are neglecting it. In strength, it will be different. But in density, thermal conductivity, electrical conductivity, even though some voids are there, they don't matter. But voids must be included in calculations of volume fractions. Volume fractions. Do you understand? Volume fraction. Because voids are there. 1% voids are there, 2% voids are there. In the volume fraction calculation, voids will be there. In the density conductivity calculations, they are not there. So let us proceed. This is the first time maybe that you are looking at it. It's a very simple rule. We are not going through the definition and so on, derivation and so on, right? So once the derivations are out, then there's a very simple rule. It's not big, but the derivations, the people may have worked 10 years, 20 years, 50 years before they found out that this simple rule really works well. Behavior under stress. We are talking of strength first, right? Relationships for mechanical properties are often more complex, right? For conductivity and density and so on, simple rules based on the previous page, but for mechanical properties may be more complex. If quality of bonding between the fiber and the matrix is sufficient, they elongate at the same rate under stress and experience the same strain. This is called the iso-strain condition. You see, there is matrix, polymer, and we have lots and lots of threads or fibers inside. If the bonding between them is very good, then we assume now that this whole composite is one material. So it stretches or elongates at the same rate, right? Because the bonding between the fiber and the matrix material is strong. So if the fiber stretches, then the matrix material also stretches at the same rate. So if that wet out is very good, the bonding between the fiber and the base material is very good, then the whole composite is behaving as a single material. So this condition, if it is followed, then this is called iso-strain condition. A strain on the matrix, a strain on the fiber is the same, iso-strain, right? So if this is the condition, then things will be simple. If it is not the condition, then we will have a little trouble. Okay.